Not really. Okay. So the second example, 2a. Part 1. State, I'll just write K for short, Kirchoff's first law. So what's his first law? Which law is that? The loop one. So it's the voltage around any loop should total 0. I'll skip part 2 for the moment. I'll go back to it in a moment, okay? And then part 3 is state Kirchoff's second law. And what's the second law? Well, that's the junction law. So the total current into any junction should equal 0. Now, part 2 and part 4, they'd like you to explain what principle is being used here. So what they mean by that is, for his loop rule, if I say the total voltage is 0, is there any physics principle you think that can use to explain that? Like, why do you think the total voltage should be 0? Well, the reason is this. If the voltage drops, what is the reason for something to lose its voltage? Like, if the voltage drops, what would be the reason why?
Resistance.
Yeah, but why would the resistance drop the voltage?
War.
Yeah, so in other words, when you have like a resistor or a light bulb or something, the voltage drops as it passes through it. That's because work is being done. So when the voltage gets all the way back to the start, there should be 0 left. And again, it's so that the reason for that is that, okay, let me give an example. Right, so do as you can. Okay, so if I drink this, energy goes in, and then I can do some work, and energy comes out. So his loop rule is like this. You start off with a voltage, and then as you move around, what do? You minus all the resistors. So you notice that the energy I put in must equal the energy that comes out. What's the name of this in physics? Conservation of energy. So in other words, his loop rule comes from the conservation of energy. Now, probably more difficult though, the current. So why must the current that goes into the junction equal the current that comes out?
Because it's closed circuit.
Yeah, it's closed, yeah.
It's charged. Those are charged. It's charge that's flowing.
Yeah.
So the amount of charge that goes into a point has to be equal to the amount of charge coming out.
There's no way that it can leave.
Yeah.
So we have to give this principle a name. So, looking at my answer from part 2, what do you think we could call this idea? Conservation of charge, yes. But I like your keyword, Kurdi, the fact that it needs to be closed. Okay.
Charge or energy?
Oh, sorry. Yes, charge. Okay, so 4 marks for all of that. Okay, can I scroll down? Yep, okay. So now, this is another circuit one, like what I just previously did. So here, now there's one here, there's one here, there's a resistor here, here, here and here. 6, 3, 8, 2. There's one here, 2. There's a battery here, 11. There's a battery here, 7. And there's a battery here, E. And the current here, 0.5. Here, I1. Here, I2. Yep, that's all of them. So here, I2 as well. So here, I1. So here, I1. This is I2. That's 0.5 as well down there. Okay, so that's as much as I can draw in. Yes.
The battery in the Mini?
We don't know it. What? Okay. First part. It's 11, yeah. First part. Simplify and redraw the circuit showing single resistors and their values that can replace the series and parallel combination. So the first thing you notice, you see these two here? These can be replaced with one resistor. So look, I need to remove. So do you have this drawn? Okay, so the first one I'll remove is this one here. A 2 and a 2, they go together and the total will be, yes, 4 there. So that one up there is gone. And then what about these two? I can put them together as well. 1 over R equals 1 over 3 plus 1 over 6. 2. Oh yeah. So I'm going to remove this one now. And then this one here now is a 2. Now, actually, I think I can go further because I think I can put the 8 and the 2 might be able to go together. I don't want to put too much together.
But then wouldn't you need to add the subs as well?
Yeah. I'll check how much they simplified in the marking scheme because it's 5 marks for this. I've already put 2 of them together. I feel like I should be able to put something else together. Maybe the 4 and the 8, I should put that together too. But let's see what they do. There it is, isn't it? Yes. Alright, so how far do they go? No. That's what I have, isn't it? A 4, an 8 and a 2. Yeah, so they stop there. Yeah. I see the question's only 5 marks, so I didn't want to be doing it too much.
You took your time.
Okay, so that's 5 marks. Can you focus here? Yes? 5 marks. Now, next part, they want you to calculate the I1, the I2, and the E. Total 8 marks. So I need Kirchoff's rules again, just like in the last example. Okay, so let me start now.
Resistor or E?
That's an E, not a tree. Okay, that was 5 marks. Now, Kirchoff's rule. If I start at this battery here of 7, is there any way I can avoid going through the other batteries? No, I have to go through them, unfortunately. So let's... Yeah, but I'll need 3 formulas for 3 unknowns. So I'll need 1 junction rule and 2 loops. So let's start with the 7. 7 goes all the way around. Now, what happens when the 7 hits this battery? Does it gain or does it lose voltage? It depends which way it's pointing. So in this case, the battery's positive is connected to its positive. You're right, so it loses here. Because if you want batteries to add together, you have to go negative, positive, negative, positive. So it loses in E. And then when it goes through this one,
Minus
it loses 8 multiply,
0.5.
yeah, so it loses a 4. And then it goes through this one, minus 4, I1 equals 0. Good, okay. Now let's do the next loop. Let's use this one here and go all the way around the outside. So we start off 11, and then what happens when it hits this battery? Lose 7. And then when it hits this one? Be careful, plus. Because the current is going towards you, the opposite direction, see? Because we're going around this way. And then with this battery, plus or minus? Sorry, I'm going around the outside, haven't I? So back to here, minus 2I2.
So isn't the current like going like to the battery?
Are you talking about the second one here?
Yeah.
I'm starting here and going outer ring.
I mean, when like the first current.
You're free to choose whatever loop and whatever direction you want. So if you ever move against the current, it actually adds to your voltage. Yeah? Is that your question, basically?
Yeah.
Yep. Okay. And then now we've used a junction rule. So what current is going into this junction? 0.5. And what's coming out? I1 minus I2 equal 0.
So can we just say I1 plus I2?
Yeah, now we have to clean these up a little bit, see what we got here. So my first equation, I get 4I1, if I take that over there, plus E, and then keep this to on the left-hand side, equals 3. This equation here, so that's a 4. So 2I1 minus I2 2I1 minus I2 minus 2. When I simplify this, I kept the I1 on the left, the I2 I kept on the left, and then I took these to the other sides, it became minus. And then divide everything by 2. And then this last one here, be I1 plus I2 equals 0.5. So what would be the easiest ones to put together? Well, that would be these two here. The matrix method, elimination, whatever. So we'll solve that. So you got here I1 equals minus 0.5 and I2 equals 1. And you can put them in there to get the E, which will be 3 minus 4I1. So that'd be 3 plus 2. So that'd be 4.
5.
3 plus 2 is actually 5, yes. I should make note of that. It might come up again.
Somebody did that yesterday. We were clapping for someone who did really simple maths.
Same guy.
Same guy, yeah. Okay, well.
Same guy?
Yeah.
Me?
No. Up and
David.
All right.
Did 2 plus 2.
2 plus 2 equals 4.
He's a physics
I
student.
know, right?
It was when we were doing the active reading thing yesterday.
Oh,
when I
yeah,
asked you
yeah,
a question,
in
it was
chemistry.
just like, it was just really simple.
They're making fun of you.
No, and I'm trying to remember
I
which.
can't remember when.
And active
It was
listening.
just before it ended.
It's okay. I believe you when I say he does things like this. It's okay. Right. So there's 8 marks for that question. Getting those 3 answers there. So, you know, I think that's a pretty good question. Now, there's only two 1-mark parts left. What is the quantity of electric charge that flows between B and A along the path through the Age Resistor in 2 minutes? So in other words, how much charge is going through the Age Resistor? So if I look at my diagram, that's the one in the middle there. So what current is going through that? 0.5. So do you remember the formula? Q equals IT. The I here? 0.5. And the T would be, if it's 2 minutes, how many seconds? 120. So that would be 60 coulombs. And the very last part is what's the voltage here? So how do I get the voltage in the resistor? Ohm's law. So what's Ohm's law? V equals IR. And again, we're talking about this one here, okay? What's the I here? 0.5. And the R? 8. So then the voltage will be 4 volts. So that last bit there was just Ohm's law, but for just this resistor. Only 2 marks, okay, for this last 2 parts, 1 and 1. Yes? Can I close this? Yep.